30 hours before the blockade was announced, something was already quietly watching from above. It was not a satellite, because satellites drift in orbit. It was not a warship, because ships need refueling and crew rotations. It was a machine, circling at about 40,000 feet, continuously transmitting heat signatures and hull profiles along Iran's coastline to a command center thousands of miles away. It had been there all night. Through the operational briefings, through the very moment IRGC commanders believed their boats were ready. By the time the first fast attack craft cleared the harbor entrance, that machine had actually been on station for 31 hours. It already had the hull count, heading, and engine temperature of every vessel still tied up at the pier. All of that data had been fed continuously in real time into a targeting network, where the strike solution had already been calculated, confirmed, and distributed to every shooter in range. By the time the boat started moving, the answer had already been sent. Iran had missiles. Iran had mines. Iran had an entire doctrine built over 5 decades to deal with exactly this scenario. But none of it accounted for an eye that had been open long before the fight began. 30 hours. That number was the answer to a question Iran never thought to ask. How do you defeat a blockade enforced by something that never sleeps? Not 30 fighters on combat air patrol, not 30 warships standing in line, but 30 hours. The baseline endurance of a single MQ-9B Guardian before it has to rotate home. One machine able to orbit a coastline that long without blinking, without fatigue, without creating a gap in coverage during handoff. The blockade did not truly begin when the order was given. It began when that machine arrived on station. This is the kind of power that never ends up on the cover of a military magazine. People usually count ships, fighters, and missiles. But in this story, what matters is each passing second. And what made the blockade of Iran in April 2026 not only possible but sustainable was an invisible architecture of steel, sensors, satellites, and software. By April 13, 2026, the United States had established a naval blockade on every Iranian port. A carrier strike group was operating in the Gulf of Oman. More than 100 aircraft were deployed across multiple forward bases, and Iran's coastline was sealed behind a dense wall of technology. But Iran was not a passive target. For nearly 5 decades, it had been preparing an asymmetric answer to U.S. naval superiority. The IRGC Navy, with hundreds of fast attack craft, shore-based anti-ship missiles, coastal defense batteries, and mine-laying submarines, was built around a very clear doctrine: swarm, overwhelm, and deny. That doctrine was not irrational. U.S. warships are expensive, large, and cannot be everywhere at once. All you need to do is find the gaps, move fast, and strike before the other side's response arrives. In military strategy, that way of thinking is tied to the loop of observe, orient, decide, and act. Every military force has such a loop. Every decision cycle has its own speed. The slower your loop, the more vulnerable you become. The faster your enemy's loop, the more irrelevant your plan becomes before you can execute it. Iran's entire asymmetric gamble rested on one assumption. In the narrow, crowded, cluttered waters of the Persian Gulf, it could move faster than U.S. sensors could track, and it could send a swarm toward the target before the U.S. response arrived in the right place. What Iran did not foresee was that the answer to that assumption had already been built. Not a faster warship, not a more powerful missile, but an invisible, distributed, almost permanent network that left Iran's decision loop behind before the first boat ever left the pier. That network is called JADC2, Joint All-Domain Command and Control. To understand what it does, we have to begin with the least glamorous part: 30 hours of continuous presence. The MQ-9B Sea Guardian is not fast. Cruising at around 210 knots, it cannot catch a speedboat, and it cannot chase down a missile. It was not built for air-to-air combat. But in a long blockade, it can do something far more valuable. Watch continuously for more than 30 hours from 40,000 feet above the effective engagement ceiling of most shoulder-fired missiles, in darkness, in rain, without fatigue, without distraction, without needing rest like a human crew. Of course, the operating limits are real. Flying at that altitude keeps the MQ-9 outside the danger zone of manpads, but it still remains within the kinematic reach of more powerful integrated air defense systems, such as the Bavar 373. The mitigation is not speed, but geography. The MQ-9 orbits in international airspace, outside the published range of Iran's shore-based batteries. If the threat radius changes, the orbit shifts with it, while the sensor coverage remains intact. That is a deliberate trade-off. You give up speed in exchange for something more valuable in a long blockade: unblinking presence. A fighter pilot, no matter how good, can usually stay on station only about 6 hours before fatigue becomes a real risk. When one aircraft leaves and another comes in to replace it, there is always a gap, a period when coverage over that area is reduced. In a war of attrition, and a naval blockade is exactly that by nature, gaps are not just scheduling inconveniences. Gaps are the enemy's strategy, and a permanent eye is what erases that gap. Each Sea Guardian flying over the Gulf of Oman carries a multi-mode maritime surveillance radar along with a high-definition electro-optical and infrared system, continuously sending real-time video, optical data, and thermal data back to command centers far away. A UAV orbiting over the Strait of Hormuz is not exactly a hunter in the traditional sense. It is more like a lighthouse, except it sends data instead of light. And that data can reach the shooter in the time it takes to blink. Picture IRGC fast attack craft starting their engines inside Bandar Abbas harbor, maintaining radio silence, emitting no transmissions. From 40,000 feet, the Sea Guardian's infrared sensor detects 30 separate heat signatures rising in a pattern inconsistent with any commercial traffic profile. Classification happens automatically in less than 2 seconds. The data package, engine count, hull profile, estimated course vector, is pushed through encrypted data link into the ABMS battle cloud. 2 seconds. That is the delay between the moment a crewman turns an ignition key and the moment a command center hundreds of miles away already has a complete targeting picture in hand. At that point, the boats have not even left the dock. The MQ-9 does more than watch. It watches, classifies, and when conditions are right, it can kill from that same orbit at that same altitude without ever leaving station. Armed with AGM-114 Hellfire missiles designed for armored targets but proven effective against fiberglass hulls and outboard engines, the Sea Guardian can function as both hunter and killer. It detects the swarm from above, classifies each boat, and starts neutralizing lead elements before the formation can achieve an effective attack geometry. And the evolution did not stop there. In 2025, General Atomics unveiled the next step, a 25-kilowatt high-energy laser pod for the MQ-9B airframe. Core components have already been tested on the ground and on airborne platforms, while full integrated flight testing remains underway. No loud explosion, no missile trail, just a focused beam from an altitude beyond the reach of manpads, intended to burn through sensors or fuel lines, one boat at a time. Iran's swarm doctrine assumed the swarm would survive long enough to close with the target. The MQ-9 was the engineering answer built to destroy that assumption. For decades, the E-3 Sentry, with its distinctive rotating radar disc mounted on a modified Boeing 707 fuselage, served as the nervous system of American air power. That spinning radar could cover a radius of more than 250 miles, command the air battle, and track hundreds of contacts at the same time. In its era, that was extraordinary capability. But the E3 has a weakness that is both mechanical and fundamental. The antenna must rotate about 6 times per minute. In other words, the radar only comes back around to update each tracked contact about every 10 seconds. 10 seconds is the distance between knowing and not knowing. In modern naval warfare, especially in narrow, crowded waters like the Strait of Hormuz, 10 seconds is dangerously long. The E3 works like a mechanical clock, sweeping one tick at a time. Now look at the problem from the perspective of an IRGC operations planner. You have 30 fast attack craft. Your mission is to close on a U.S. destroyer before the other side can vector supporting fire onto your position. Under the E3's 10-second sweep cycle, each boat can cover roughly 200 meters between radar updates. That is 200 meters of relative blindness on the screen. Enough to change course. Enough to split the formation. Enough to disappear into a cluster of fishing boats where mechanical radar struggles to distinguish military targets from harmless maritime traffic. But under the E7 wedge tail, that window shrinks to a fraction of what it once was. And once it shrinks far enough, it is no longer a gap. It becomes a trap. The E7 wedge tail, the aircraft the U.S. Air Force is now transitioning to as it gradually replaces the E3 fleet, carries something that does not need to rotate mechanically: the MESA array, a multi-role electronically scanned radar built by Northrop Grumman. Instead of turning the beam with moving hardware, MESA steers radar energy electronically at speeds measured in milliseconds. The update rate therefore drops from 10 seconds to a small fraction of that time, fast enough that a fast attack craft running at 40 knots has almost no room left to maneuver between sweeps without being tracked continuously. Even more important in the Persian Gulf environment, the MESA system can separate moving military boats from sea clutter through Doppler processing. In physical terms, ocean waves are relatively stationary compared to the water surface. An IRGC attack craft is not. The E7 processes that velocity difference to separate signal from noise in a shallow, crowded, chaotic littoral environment in ways the mechanically scanned E3 simply cannot match. Of course, the limits in fleet size are real. The U.S. Air Force is still in the transition phase from the E3 to the E7, and the current wedge-tail inventory is still in the single digits. Each airframe, at this stage of fleet development, is almost irreplaceable operationally. Lose one, and the tracking network develops a very real blind spot. But in a blockade, you do not need a dozen of them. You need one in the right place, at the right altitude, at the right moment. The data a single E7 produces can multiply the lethality of every other asset in the theater at once. In this architecture, one E7 can provide situational awareness over more than 4 million square kilometers per mission, roughly half the landmass of Australia, while feeding near real-time targeting data to carrier strike groups, destroyer formations, and F-15E squadrons operating across 3 separate bodies of water. That is not just a sensor. It is a thinking radar, the nervous system of an entire theater of war. But a radar that sees everything becomes useless if the aircraft it guides run out of fuel. And fuel, in a blockade that lasts for months, is the variable nobody puts on the cover. Nobody makes documentaries about tanker aircraft. The KC-46 Pegasus carries no weapons. It cannot defend itself like a fighter. It has no radar cross-section advantage, no targeting pod, no stealth shaping. On the outside, it is just a gray-painted Boeing 767. But what it carries is more than 212,000 pounds of jet fuel. And that single logistical fact is enough to separate a blockade that holds from one that quietly collapses at 3 o'clock in the morning. A fighter without aerial refueling is like a sprinter without legs for the long distance. It performs beautifully for the first 100 meters, then it stops. The blockade of Iran's coastline did not need sprinters. It needed marathon runners, assets that could hold over a contested choke point not for a few hours, but for the duration of the crisis. Look at what happens without tankers. AB-52H flying from Diego Garcia to lay mines near the Strait of Hormuz has to cover roughly 3,300 nautical miles each way, nearly 13 hours of flight one way. That bomber cannot make the round trip on internal fuel alone. It needs aerial refueling, multiple KC-46s positioned across the Indian Ocean to top it off on both the outbound and return legs. Remove that refueling chain, and the mission does not become weaker. It disappears completely. The mines do not get laid. The approaches to Bandar Abbas remain open. And any IRGC planner who has studied U.S. patrol patterns would know exactly which missions vanish the moment the tanker chain breaks. The KC-46 does not just keep aircraft in the air. In many cases, it is the only reason some aircraft can reach the fight at all. Now look at the economics. 1 hour of KC-46 flight time costs tens of thousands of dollars. An Arleigh Burke Flight 3 destroyer, the kind of ship that tanker chain is indirectly protecting, costs more than $2.5 billion per hull. If the tanker chain is interrupted for 6 hours and an IRGC swarm finds that gap, the math practically writes itself. Commanders often use the phrase, "however long it takes," to signal resolve. What that phrase does not say, and in fact cannot say, is that it expires the moment the fighters hit minimum fuel, usually after roughly 4 hours on mission. Remove the tanker chain, and the blockade suddenly has a hard deadline nobody wants to mention. Keep that chain running, and however long it takes becomes a physical reality rather than a promise. Logistics here is not just background support. In a long naval blockade, the fuel chain is the weapon. Once all three of these vectors are held at the same time, the picture changes completely. An eye that watches without sleep, a nerve center that processes targets through maritime clutter and updates faster than any mechanical radar, a fuel chain that turns continuous presence into something physically sustainable. Each capability on its own is impressive, but together, they do something no single weapon system can do. They erase the very conditions that allow Iran's strategy to function. JDC-2 is not a weapon in the traditional sense. It is a kill web, a network of destruction that removes the adversary's room to decide. The MQ-9 means you cannot launch without being seen. The E-7 means you cannot maneuver without being tracked. The KC-46 means there is no window of opportunity, because the aircraft watching that window never has to leave for fuel at the moment you need it gone most. What remains has already been demonstrated in exercises and trials such as RIMPAC 2024, Northern Edge, and integration events in the Norwegian Sea. In this architecture, sensor-to-shooter latency has been compressed down to a matter of seconds. Detection, classification, weapons assignment, all of it happens so fast that a fast attack craft may only have time to travel its own hull length. Of course, the limitation must still be stated clearly. JADC-2 is not yet fully mature in a heavily denied environment where sustained electronic jamming and GPS spoofing are constant. In those conditions, latency increases and the kill chain slows down. But slower than perfect is still faster than an opponent forced to make decisions manually through multiple layers of command in a structure built for another era. And that gap, measured in only a few seconds between sensor detection and weapons release, is the foundation of the entire blockade. JADC-2 does not win by adding more weapons to the battlefield. It wins by compressing the time between seeing and shooting until the adversary's weapons become irrelevant before they can even be used. John Boyd, the Korean War fighter pilot who first described the loop of observe, orient, decide, and act, argued that the faster decision cycle wins every engagement, regardless of firepower. JADC2 is that theorem applied at theater scale. That is not just air superiority. That is decision superiority. And decision superiority is the destination of every design choice we have examined today. A persistent eye at 40,000 feet beyond the reach of manpads, an AESA nerve center separating military signals from sea clutter, a tanker chain that turns however long it takes from a slogan into reality. The blockade of Iran's ports was enforced by warships, fighters, and bombers. That is the visible part, the part photographed by the press from carrier flight decks. But the architecture beneath it, the persistent ISR layer, the AESA tracking center working through Gulf clutter, the logistics chain sustaining 24/7 presence, the AI-enabled kill web fusing sensor feeds into a tightly compressed decision loop. That is the invisible part. And it is precisely that invisible part that made the blockade hold. A senior CENTCOM official once said the blockade would continue however long it takes. That statement only has real physical meaning because of everything we have just examined. And that is also the question JADC2 forces every future adversary, not just Iran, to face. If moving means being detected, acting means being targeted, and responding means arriving too late because the loop is already closed. Do you still have a real navy? Or do you simply have a pile of expensive hardware rusting at the pier, waiting for a window that closed before you ever knew it existed? That is the nature of this new kind of power. People no longer just count ships, they count seconds. And once every second has been seized, the kill web has in fact already been running long before the first shot is fired.